Hey there, folks. So, last episode we finished up our campfire actor. We went through, added a light, and we started work on making adjustments to our. Brain's not working. Statline component to allow and account for things like ambient temperature and local heat offset. So, this episode, I do want to continue on with that. And really, we're going to be focusing pretty much purely on the stat line component, and a good majority of this is going to be code. So, with that, we're going to get things started here. I'm going to drop out of the editor. I was running through Visual Studio just because I wanted to get a build done so things didn't take too long this go round. So, one thing I'll point out quickly, I did between episodes just go through and do some organization within my header files. Specifically on the stat line component because it was getting a little messy. You can see here I added the stats into their own region and categorized them within the UI. I did the same thing for anything movement related. And just to say, I included moving functions in there, and that's just to, like I said, add some organization in there. And we're going to start work again, as I mentioned here, in the temperature section. Now, there is going to be a lot of math involved in this episode. Hopefully, editor me can manage to do it, but I have various spreadsheets and numerous pieces of paper that I've been trying to do the math for this on. I'll hopefully include a screenshot around here. But with that, though, as I said, there is a ton of math involved around this. I don't specialize in thermodynamics or anything like that. Heat transfer, I looked into it, and that is a very, very complex equation for when you're looking at doing stuff like this. And I think I've simplified it as much as I could. So, to get started, though, obviously the very first thing we're going to need is the current body temperature. Float current body temperature. Now, because I'm working in Fahrenheit, it's got those fine tunability there, finer temperature range control sort of thing there. I looked it up. Average human body temperature is between 97 and 99 degrees Fahrenheit. We're going to cut it right in the middle and do 98 degrees Fahrenheit. And that's not degrees Fahrenheit. That is just to confirm this is a float. Actually, here, I'll do that to be precise. So, there is a couple other factors we're going to need to take into account. Your character can have thermal insulation. Now, you could break that down into a generic thermal insulation, but you do have certain things that are better at keeping you warmer and certain things that are better at keeping you cooler. So, for example, winter coats. You wear one of those in the summer, you're going to overheat. So, I'm going to break down my thermal insulation into two different categories. And it's going to be heat insulation, and then another one which is going to be cold insulation. Now, the next one, and this is actually where I started running into some really complex issues when it came to the math, is, well, you may have a winter coat on, but if that's all you're wearing, you've got your legs completely uncovered, your head completely uncovered, you're still going to end up losing, but standing there, you're still going to end up losing heat. So, there was another one I needed to add. Body coverage, and that is to indicate how much of your body is naturally covered. Actually, I'm going to put these at 0.0 to help protect from things like wind chill and the likes. Now, there was, I'm trying to think, was there anything else? Oh, yes, there was one other one. I was just looking over my notes. And because, so this is a generic one, generic setup. The stat line is used on things. I'm just going to use example from a mouse, a deer, a human, an elephant, a polar bear. I'm just using these as an example because this is a generic stat line component that is going to be handling temperature. You're going to need a way to indicate that, let's say, a mouse is going to lose heat a hell of a lot quicker than an elephant or a polar bear is because of body mass. So this was the other one. And float adjustment factorial equals, and I think I started around 500 for this, but my paper math on this, I was getting some really weird numbers. So now we've got those basic ones in there. We're going to want some functions to handle this. So the first one we want is a void update body temp const float reference delta time, obviously because this is going to be happening on tick. Actually we want current body temperature to be edit defaults, because certain things, as mentioned, like a mouse and a polar bear, are going to have different body temperatures. But because right now we only have a human character, I'm defaulting it to 98.0 degrees Fahrenheit. And then the other thing is, because we have these two insulation values, we are going to need to have some functions for adjusting those. Void add heat insulation. Actually, I'm not going to adjust heat insulation. Const float reference amount. And void adjust cold insulation. Const float amount. So those are the three functions I determined I was going to need. So let's quickly define these. This update body temperature one gets a little messy, so we're probably going to spend quite a bit of time working on that one. So these adjust insulation ones are pretty easy. So it's heat insulation plus equals amount. Now, with my logic and how I mapped this out, that's actually not going to work. But that's what everyone would normally do. It's like, oh, I'm going to add an extra 2 points or 5 points or whatever. I'm not treating heat insulation as like a temperature offset. It's a percentile is how I want to do it. So I wanted it to have a value of 0 to 100. So fmath clamp heat insulation plus amount 0 or 100. And like I said, this is a I'm going to be using it as a percentile, because basically I could go, and this is where I was stumbling with the math, is you could go through and it's like, okay, your current outfit has a temperature rating of up to minus, well, we'll say 32 degrees Fahrenheit. That's freezing point, I think. 32, yeah. Either way, 32 degrees Fahrenheit. So anything 32 degrees and above, it's going to ignore. 32 degrees and below, it's going to adjust. So if you've got a 32 degree Fahrenheit outfit and it's 20 degrees Fahrenheit, well, you got a 12 degree offset there that you need to account for. And that's where my math was getting really complex and very complicated. And I didn't want to go down that route with that. So instead, I decided it's going to be a percentile. If you have a heat insulation of 100, technically you're never going to overheat. If you have a cold insulation value of 100, you're never going to get cold. However, And I understand. It's like, well, that's not possible. That is going to be determined by the equipment the player is wearing, or the character is wearing, because this is also going to affect the AI characters. And realistically, you should never be able to have a combination of items that are going to give you that 100 points of insulation. So that's the reason why I went with this approach, just because the math was getting insane. So let's look at my notes here. So this one I'm going to be typing out, and it is going to be a lot of internal variable declarations and stuff, just because this math is that complex. So the first thing we want to do is float effective world temp. And that's going to be the current ambient temperature and the current local offset, current local temp offset. So if we're out in the middle of nowhere, we don't have a fire nearby, this is going to be 0. Effective world temperature is going to be this. If we're standing next to a fire, it's going to be the current temperature plus the offset of the fire that's providing some heat. And that's basically going to be the immediate temperature around the actor. Now, the next one is that insulation value. Now, here, this is just a quick one to determine which one we need. Value equals effective world temperature less than or equal to current body temperature. So what we're doing here is we're just going, okay, if the effective world temperature is colder, we're going to use our cold insulation. If it's hotter, we're going to use our heat insulation. And I made the decision, because we're always radiating heat to lose heat, that if they are identical, so 98 degrees, then it's going to consider it as a thermal radiation. So it's going to be, we're going to use the cold one here. So with that, cold insulation, otherwise heat insulation. All right, so now we need to get that, as I mentioned, a percentile. Insulation value divide equals by 100. And that's just going to give us a value from 0 to 1 is what that's going to result in. So now, float, and this is just so we can actually do some continual comparisons. Adjusted temp equals effective world temp minus effective world temp multiplied by that insulation value. So what we're doing here is not minus, effective world temp multiplied by that. So with 0 insulation, meaning we're just going to say that the player's standing out there with no clothes on whatsoever, this is going to have a value of 0. So effective world temp, we're going to say is 50. Well, 50 times 0 is 0. Effective world temp is still 50. So this is a catch case that is going to need to be expanded. I'm going to do this in a later episode because this is some logic I decided I didn't want to try and account for, and that is, as I was mentioning, exothermic animals. Sorry, I had to sit there and think for a second. So you've like exothermic versus endothermic. We produce heat naturally from our metabolism, but if, and I didn't want to account for that, adjusted temp less than or equal to 0. This should never be below 0. It should always be at most 0. But just in case I threw the less than, if there's some float point math error, that means did I do that right? Adjusted temp. Oh, yes, sorry. That is meaning you're 100% insulation. However, we could, as I was mentioning, could just throw it in here if insulation is equal to 100. Return. I didn't want to do that because, as I was mentioning, you do have naturally radiating body heat from a person, and for the purpose of this game, I'm not going to say if somebody's an endotherm or an exotherm. Everything's going to be an exotherm, but because of this, that I didn't want to do this where you're just going to say, okay, we've got max insulation, we don't care. What I wanted is this here. This is going to be to do add in natural body temp gain. Actually, no, not gain. Temperature balance. Temperature balancing. And that's going to be like, okay, if like sweating to overheat because you're overheating, or shivering because you're cold, and it's going to make like those temperature adjustments. But for now, that is just going to lead to a return. We don't want to adjust our character's temperature from here. So the next thing is we want to get our difference in body temperature. So float difference in temp. All right, sure. I'm going to use full names just for ease here. And this equals the current body temperature minus the adjusted temperature. And this is going to give you a range. So if the temperature is over your body temp, you're going to end up in the negatives. If your temperature is below your current body temp, it's going to be a positive number. Now, let's see. This is something you can add if you want. And this is going to be for things like ignoring such a small difference in external and internal body temperature that you don't want to adjust anything. So float current, temperature difference to ignore. And I'm going to set this something pretty low. Like I only want it to be within, say, 5 degrees Fahrenheit. And this I'll probably tweak. Again, actually, we want to make some of these edit defaults only, so we can adjust them in the blueprint. Add that there. Add that there. Body coverage. We need a variable, a function for that as well, actually. Adjustment factorial, we want it to be edit default, and we want that to be edit default only as well. So what we want now is if difference in temperature is less than or equal to temperature range to ignore. Again, we're going to have a return. We don't want to do any further math. And you can refactor this to be a lot more efficient. I'm doing this for debug purposes, so I can step through all of this, figure out what's going on, and make tweaks as needed. So now this is where this factorial comes in. Adjustment factorial. And this is where I found no matter where I went, these values were still getting, for the purposes of losing body heat or gaining body heat, were pretty drastic. And one thing I was toying with here, and I haven't experimented with, is you could potentially, instead of having a fixed factorial, you could have like a float curve. That the higher the difference, the lower your factorial, things like that. But I haven't gone there. That's something when you start fine-tuning the systems, you would add. So now what I want is difference in temperature divided by divide equals by the adjustment factorial. And now this is where body coverage comes in. So if body coverage does not equal 0, because you don't want to do any divide by zeros, it causes weird math errors, and well, computers don't let you do them. Divide by 0 is just a bad thing. Difference in temperature, again, divide equals by body coverage. And this particular order of operation, they do play a fact, because like this is just a global. Like I want to say the human body is better at retaining heat than a mouse's body. The body coverage, again, that's something that you want to apply after, because that's representing your clothes. This is representing your person, like your physical body. Body coverage is representing your clothes, so you want to do that after. And then finally, because we don't want this to be happening every frame, this base amount, we want that to be multiplied by delta time. So difference in temperature times equals delta time. And then finally, we want to actually adjust our body temperature. So current body temperature equals, and this is where this one still comes into play, because you need to do some either plus or minus math. So effective world temp less than or equal to current body temp. It's going to be current body temp minus difference in temperature. Otherwise, and actually I'm going to format these on separate lines. Current body temperature plus difference in temperature. So just to work through this, and like I say, this right here is one I wanted to address in a later episode. I still have some math to do and some other things. Also, something you're going to want to factor in is, are they sprinting? So we could look at our movement one here. So is sprinting, you're obviously doing physical exercise, you're going to generate more heat. So you want to add in something for that. I'll be factoring that in the next episode as well, just because this is getting really complicated. And like I said, the amount of math I've done for this is, I don't think I've done this much math since high school. So, but anyway, so now we have, just to go through here, we're calculating what is our effective temperature. That's taking our world temperature and any local temperature offsets we've got. We have our insulation value, which is basically, okay, are we standing in the cold or are we standing in the heat? We're getting a percentile of that, and we're using that to adjust our effective world temperature to meet to determine, like, is this like how far off are we comparing the insulated temperature to our body temperature? And terminology is really going to be weird on this one. And so from that, then we are, that's not current, that's not what we want, that's current body temperature. And this is where rubber duck programming comes in. So to explain rubber duck programming, it's actually what I'm doing right now, or rubber duck debugging. You have your code and you walk through and you're explaining it to, in most cases it was a rubber duck is where it originated from. It could be a coworker, it could be, well, in my case, I'm recording for a video and I'm talking. It could literally be a rubber duck or an action figure sitting on your desk. But right here, I've got an issue. That is not current ambient temperature. That is current body temperature, if I remember correctly. Let me look at my notes here. Oh, yes. Yeah, current body temperature. So we're going to copy that. Yeah, so whenever you're having a problem, It's one thing I do all the time, whether I'm recording an episode or not. I'm actually glad I caught that, but it's to talk through your code, explain what's happening as you go through, and you're going to catch weird things. Like here, it's like, oh, ambient temperature. Well, that's what adjusted temperature is. So anyway, so we're going to get current body temperature. If the actually, this needs to be changed to an absolute, thinking about it, because if we'll just say temperature is 100 degrees, so we're going to be positive 2. We have 0 insulation, that's going to be positive 2. Difference in temperature is going to be 98 98 minus 100, so that's going to be negative 2. We're going to pretend this is 0. It's negative. That's going to be a negative. It's still going to be a negative. Well, actually, we'll have to test that. I'm not 100% sure. I think we might not need this fancy one. It could just be current body temp minus difference in temperature. But anyway, so we're getting that. So this is our difference between our body heat, the body heat and the insulation adjusted ambient temperature, which is the adjust temp. We have a threshold of if we're going to say, okay, anything smaller than this degree, we're going to ignore. Then we're adding in our adjusting by our factorial. And the reason for this is right now, this number is going to be pretty high, even when it's adjusted by delta time, within factoring in body coverage. So if you have 0% body coverage, you're going to be subjected to the whole thing. If you have 100% body coverage, and this isn't going to be 100, it's going to be, I think I did the math with this, is a range of what, 1 to 7, 0 to 7. So it's like I broke the human body up into roughly 7 quadrants. Left leg, right leg, lower torso, upper torso, left arm, right arm, head. I'll actually add that in here before I forget. No, I'll put that at the end of the... No, valid value. So let's say, and just using that for a quick example, you put a pair of shorts on that is half coverage on the left leg, half coverage on the right leg. That's going to just be a total body coverage of 1 to represent half left, half right. Actually, technically, no, it was 8 because I had the torso into 3 parts. Technically, it would be 3. Lower torso, left leg, right, would be 1. Left leg, right leg would be half. So it would have a value of 2 for putting on a pair of shorts. And then we're adjusting for delta time because all of this math is based on per second. And we want it to be adjusted per tick. So that's what the times delta time is. And then we are making the adjustment as needed. So now we've done all that, and this math has caused my head to hurt already. We're going to build this quick. Let's see, how long are you going to take to build? Yeah, so this is taking a moment to build here. So I'm going to pause the video, and I will be back as soon... Oh, I say that. Let's see, is it going to... Okay, so the build works, so let's hop into the editor. And there is still a function I want to add in, as I mentioned, for body coverage. And it's going to be just adjust heat insulation. And it's going to have that value from 0 to 8 instead of 0 to 100. Excuse me. And yes, I do understand certain animals, it's not as easy to divide into 8 parts, but you don't have body coverage on animals. They're not wearing pants, they're not wearing shirts or coats or things like that. So you factor animals in by things like the factorial. Body coverage on an animal was always going to be 0. So anyway, so we're going to go in here. We're going to take a quick look at our blueprint actor for our third person character here. If it actually wants to respond. Wakey, wakey. Come on. Oh, Windows Defender is slowing things down again. All right. There we go. Okay, so we have our player character here. We're going to look at our stat line. And as you can see, as I mentioned at the start, I've grouped things up in here. I'm not too worried about those for now. But so we never concerned about temperature. We'll do that after. Right now, the only thing that's dealing with this is the player character. We are concerned about temperature. So current ambient temperature, current local temperature, current body temperature, heat insulation. Actually, that needs to be edit anywhere because we're not going to see it. Heat insulation, cold insulation, body coverage, adjustment factorial, and temperature difference to ignore. So I'm going to quickly, it was a current body temp, edit anywhere. I'm going to throw that in here to do change back to edit defaults only when logic is good. So the whole reason for this is edit anywhere exposes things to blueprints in a way I don't really want. As I've mentioned, there's potential for mod support and things like that. So anyways, going to move this out of the way, and let's do a quick live code compile. Is that going to be a small enough change that it detects? Or am I going to have to do a complete recompile? Character, consumable, heat source, actor. Yeah, it's detecting changes to the header of the stat line. So it's making the rest of them. All right, so pull this back up. Current body temperature is still edit there. Okay, we're good. So move that out of the way. We're going to hit play. Now we're just going to take a quick look for now. Stat line. Okay, well, something is falling inside a category that we don't want. So let's take a look in our tick function. Oh, I know exactly why. Derp. So, cookie to anyone who understands that I never actually call the function, or who caught that I never call the function. Tick component, we're not ticking it. Delta time. Save that, go back to the editor, and we will do another live code compile. Yeah, and this one's doing right. Only one build action this time because we changed the source, not the header. Okay. Let's modify new. Okay, let's try this again. As soon as I went to throw the breakpoint on there, I realized I never actually called the function. Okay, so there you go. You can see it's actually going down really quick. Way more than I want it to. Even with, like, it's below freezing out there, I don't like that extent. Let's go over see our fire, what it does. Light. Okay, so that puts us at about 67 degrees. So, okay, let's go through to here, and I'm going to throw breakpoint in. So, effective, ignore. Effective world temp is 67, we'll call it 68 for purpose of this. Insulation value should be 0, we don't have one. Yep. So 0 divided by 100 is still 0. So adjusted temp should still be 68. and it is. So if it's less than or equal to 0, okay, we're not worried about there. Our temperature difference is only 26 degrees, which is, yeah, that's right there. Body temperature is way too low for what it should be. That's hyperthermia. Hypothermia. We have a difference of 5 degrees. Not worried about that. So our adjustment factorial of 500, it's not going to actually show us here because of weirdness, but you can see difference in temperature drops to 0.05 once we get down here, and current body temperature drops down by 0.05. So continue here. That factorial isn't enough, and this is why I added that factorial in, because it allows you to fine-tune it per character. Let's jump that up to 1,000. So instead of being 0.05, that'll be 0.01. And 25. I think. We'll see. My math might suck. So, oh, live coding. Oh, that's not going to compile. Yeah, okay. So we can't make that change because we did some live code changes. So we're going to hop out of the editor here. Yeah, we're going to save that. And just quickly as we're hopping out, we're going to add in that extra function I was talking about here. So down here, void adjust body coverage const float amount. And this function, or these functions here, these adjust, they are set up the way they are so that they can be called for both adding and removing an article of clothing. So we'll go back to that shorts example. You add the shorts on, it's going to add, say, 2 body coverage, a positive cold insulation, and a negative heat insulation. Or sorry, positive heat insulation, negative cold insulation. So, but anyways, so in this case, a body coverage equals fmath capital M fmath clamp body coverage plus amount minimum of 0, maximum of 8. 0.0 and 8.0, just for sanity's sake. All right, so I think if there's anything else in here, actually, I'm gonna, for purposes of this, no, they're private. Do I want to? Actually, I'm going to expose these to public, and I'm actually going to make all 3 of these blueprint callable as well, just for now, for the purposes of debugging. And like before, to do, well, they need to be public anyways to be exposed to equipment and stuff like that. Might not need to be, depending how I do that system. I haven't figured that out yet, but to do remove blueprint callable on below 3 adjust functions once done debugging. And again, as I've mentioned in other episodes, little comments like this, they're helpful because, you know, let's see, task list in here. I mentioned current project, turn off, auto activate on emitter, consume fuel logic, log error. Didn't add that in yet. Didn't add that one in yet. And you see all these little notes, and you can just get there, view, is it main or is it that other window, task list. And that'll open this up, and it's very useful. And you can actually see it was used by Epic. So if you go to the entire solution, there is tons of these in here, like absolute tons of to-do notes. And they are like quite literally, this is so that you can, actually I don't think you need the colons there. No, you don't. You just need that // to do. But yeah, you can see that's used by lots of people for that, and I find it very useful. So anyways, now we've done that, let's launch back into the editor. Let's see if this is going to take too long. Oh, there we go. I was just about to say I'm going to pause, and it comes up again. So all right, we're loading the editor now. All right, so we can open up our player character. Actually, I want to make an adjustment to this so we can actually get that heat value. Max heat value 100. It's actually more realistic as well. It's going to be over 100 degrees when you're standing right next to the fire. So yeah, bump that up, and then we're going to open up our third person blueprint and our stat line, and just check 98, heat insulation, body coverage, adjustment factor 1000, temperature difference is 5. All right, so those did retain. I'm going to hit play here. Character, stat line, temperature. So you can see our temperature is dropping a lot slower. We're just above freezing. It's like what, we're all but below freezing now. So yeah, there we go, 32 degrees, we're below that. Our temperature is still dropping fast, but nowhere near as fast as it was with a factorial of 500. Walk over here, light our fire. You can instantly see now we are at what, 106. Oh, now it's not going up. So we've got some weird logic there. So let's hop into here. Okay, so effective world temp is 122. Insulation value is 0. Adjusted temp should be 122. Difference is -26. Aha. This is why. So, because we're having these issues with live code, I'm actually going to stop using it. I've been running into some more problems than it's worth. So, what you need to do here is, if you need to make sure this is abs, which is short for absolute, it changes this into a positive number. So if it's -1, it becomes 1. If it's -100, it becomes 100. And actually we can, okay, so that would be, we'll just, actually no, we're going to go back. We're going to keep debugging through this because I don't want to make assumptions yet, but I'm like 95% sure this is going to actually end up lowering the temperature as well. So, all right, let's load it up pretty quick. Okay, so we're going to go back in play. So this is something you'll notice the first couple of ticks, because not everything has updated. These values are 0. We don't want to add in any catch for that, because you could actually have a 0-degree world or a negative world. So it's very hard to catch. I just made this decision because the first couple of ticks, everything's being loaded in, everything's being rendered. We haven't broadcast any temperature yet or anything like that. So anyways, I'm going to drop this off here. We're going to start our fire quickly. Switch over to first person, it's easier. and switch back to Visual Studio, and so we're at a breakpoint. So effective world temperature is 127. Our current body temperature is 97, so we're plus 30 degrees. Which in this case actually results in a negative 30 degrees. Because of the way this math works. So we skipped over this, so we've got that. So we're going to come down here. Difference in temperature is now 0. So we have 97. What was it? Second one. Okay, second decimal. So that should, if this is correct, go to 97.49. I've got a feeling it's going to 97.45. So if you hit F10, this is the last time you can look at an internal function. It went down. No. Yeah, it went down. So, yes. Okay, so how do we want to fix that? What I'm actually going to do is we're going to get rid of this absolute here. And we're going to do that up here. Absolute of this. So basically what it means is whatever this number becomes, it's a positive value, because we're not doing any less than or equal to comparisons in this logic. Actually, no, I'm not. The reason being, and I'm sorry for that confusion there, folks, is this here is actually pretty complex when it comes to calculations in comparison to what would be current body temp minus equals difference. So what I'm going to do here is I'm going to return this absolute to where it was. And we're going to, for now, comment that out. And the reason why it's more complex is we have to do, like, imagine that this is just a, I wouldn't say simplified, an alternate way of going if current body temperature else. So let's copy this out for the purpose of this, just to explain why. So the commented out code here is effectively the same thing as this, just written as what would be one line of code. Oh, sorry, I missed a part. And ultimately, this one line is far more code efficient than this or this. Now we're talking milliseconds, not even milliseconds, like nanoseconds. We're talking for this. So, but for now, I'm going to comment that out, and remove that and leave this commented out, and we're going to give this one more shot. And I did not expect this to take nearly an hour. So again, loading pretty quick because we were just changing a source file. So changing source files, I'll cover this quickly now. Changing a source file shouldn't really affect your compile time too much. It's when you start making changes to header files, because you make a change to a header file, every other class that references that header file as an include needs to be rebuilt. So anyway, so let's give this one more try. I think we're pretty close to where I want it to be. Get rid of that breakpoint for now. Character stat line down here. Okay, we're losing temperature. I'm going to run over, stand next to it. We're still losing temperature. Okay, so we now have a positive temperature, and it is going up like it should be, not down like it was. Now let's drop. Okay, that's 100 and... Okay, we're going down. And you can find that sweet point where, right there, we're at that sweet spot where we're within that 5 degree temperature range that we're ignoring. And as the ambient temperature warms up, this will eventually switch over, and because that's what, yep, there you go. Now we're starting to warm up. We back up again. We're cooling down. So now, as I said towards the start, this is heat transfer and heat loss is a very complex equation. There is far, far, far more factors involved. There's things like sweating, if you're wet, if there's wind chill. Because I intend for a survival game ultimately, and I want to try and be somewhat accurate, like if it's windy, I want you to lose temperature more. If you're wet, I want you to lose temperature more, or like things like that. However, those are some additional things that I want to add in later on. I don't want to worry about that right now, because as I've said in other episodes, I've done my proof of concept on the core stuff. My temperature stuff was horrible when I was doing my proof of concept work. I was losing, yeah, I hyper and hypothermia was happening in seconds, not minutes, which is more akin to what I'm hoping for. Because you stand outside naked in sub-zero, sub-freezing temperatures, you're going to get hypothermia real freaking quick. So that's the whole purpose of that. But anyways, folks, sorry, I went on a sidetrack there. Going back to the whole thing, the thermoregulation and everything involved is incredibly complex. This is far from a final solution. This is far from a real world analog. If I was going for a real world analog, I wouldn't be doing it on a generic statline component, because you would not be doing that on every single character. The math involved would be insane. I'm trying to find that happy middle ground between computer friendly and real world analog. And right at this point, before you factor in wind chill, being wet, things like that, I think this is a happy middle ground. Now, because you can adjust it, so like extreme cold temperatures, a mouse is going to be more affected. Extreme cold temperatures, a polar bear isn't going to be as affected, because A, they have a lot of thermal insulation because they're got a lot of body fat normally, and their bodies are adapted for it, things like that. So that's not to say I have a polar bear planned. That's just an example of the extremes. So what I plan on with this going forwards, though, is I do plan to expand the temperature system a little more. I don't know if that's going to be in the next episode. As I said, I want to factor in things like weather and dampness, I think is the word I want to use, like how wet the character is, things like that. Like if you've, before going into a lot, because my brain keeps trying to go down the path of, okay, what would be the math for this? What would be the math for that? And that leaves me sitting here in silence, not actually talking to you guys. So with that, though, folks, as always, any comments, questions, suggestions, concerns, please feel free to leave them in the comments below. I do try to respond to all of them as soon as possible. By the time this episode goes live, I'm actually going to be back at work full time, so I'm not going to be as responsive. I do work from home, but I turn my phone off for things like that so I don't get distracted. And as before, if you do have any one-off tutorial type episodes you want to request, please feel free to leave those in the comments. The first one went live the other day. Can't remember exactly. The very first one I did, which was my material overlay I used for sculpting my landscapes, has been live for a bit. So if there's anything else, though, please feel free. I have a couple other ideas. They're not going to be related to the project. It's things like a toon shader that I found that worked. pretty easily. And some other stuff. I can't remember what they were. I've got notes on them somewhere. But anyways, folks, again, I'm getting sidetracked. As always, thank you for watching, and I will see you in the next episode. Hey there, folks. So I'll have thrown a bit of information up as a card or some text during the editing of this video, but while I was editing, I did notice there was a bug in the logic for calculating the temperature, or the temperature loss, I should say, on the player character. And I didn't want to just leave it until the next episode, simply because it's a flaw, and there is enough of an issue there that I wanted to change it. So with that, quickly, if this is going to respond for me, we're going to close out of the editor here, and we're going to hop over to Visual Studio. Okay, so where the flaw is, it's actually around this adjusted temperature. Some of you have may caught it, but this is actually doing the opposite of what I want it to do. For example, if it's cold outside, we're actually making it colder, and if it's warm outside, well, if it's a warm ambient temperature, it's doing what it should do. But overall, this logic is flawed. So I wanted to correct that because, like I said, it's a big issue. So I figured out what needs to be done here is around here. So we don't actually need adjusted temperature at all. And what we need here is the effective world temp, because we're doing the adjustment before. So this absolute is still good. This is just if our difference in temperature is within that, like, whatever we set, 2.5, 5 degrees, whatever it is, we're not worried about it. Actually, I'm going to drop that down. Where we need to make the change is here. It's difference in temperature minus equals difference in temperature times the insulation value. So with that, we'll just run through. We'll have an insulation value of 0, so we're not going to be making any change here. If we're making if we have 100% insulation value, this is going to become 0. If we have 50%, and we'll say the difference in temperature is 20 for ease. If we have a 50% coverage, this is going to become 10. And it doesn't matter what it is. Because if you have, let me pull up a calculator here just to show. So if you have, it's a negative 20 degree temperature, we times that by, we'll say we have half, so it's negative 10. And if we go negative 20 minus negative 10, it's still negative 10. So we're not worried about weird inverse math with negative values. And this is actually what we wanted. This is what I was going for. Like I said, I realized after the fact that this was flawed. I was looking at the code. It was actually when I was trying to throw the screenshots in, and I found that one spreadsheet. I realized, oh crap, I have a flaw in the code. So, well, it's not even a flaw. I have incorrect math. I'll rephrase that. So I did just want to throw that in as a very quick addendum. Just because, like I said, I didn't want to leave this till the next episode, because I felt it was important enough to fix this episode, because really this is a one-off episode here. So with that, though, I'm actually going to quickly clean this up. But anyways, folks, thanks for watching. Again, apologies. I wanted to throw this in at the end. Thanks for watching. Comment, questions, concerns, suggestions, throw them in the comments, and I will see you in the next episode.